And read it loud.
Our favorite rocket sled accelerates from a speed of 10 meters per second to 20 meters per second. The mass of the rocket sled plus the rider
So it's a rocket sled, right?
Yes.
And it speeds up.
Yes.
And we're going to assume constant acceleration.
Okay.
So rocket sled. There's the sled. There's Mutasim smiling. And there's the rocket part. Yeah?
Yes.
Mine doesn't look very good, but it doesn't have to, right? And here's the end where it's moving faster, right? So there's the rocket sled. Speeds up. Okay, what are the speeds in the beginning and end?
10 and 20.
Okay. It's not 2.0, that's 20. Okay. And then the system's the rocket sled?
And the person on Earth.
Why are you including all this stuff? Is there any change in height?
No.
So why include the Earth? The person's in the rocket sled, so they're already there.
Okay.
But you don't need the gravity field as part of your system because the force due to gravity is not doing any work.
Okay. Because it's flat on the ground.
Yeah. Oh, we lost Cynthia. Everything good? Oh.
I wanted to check out.
Okay, it's all good. It's all good. She's cool. So K1 is less than K2. You guys notice that? UG, we don't care because it didn't change. Or you could say that the rocket is still at the UG reference line, so UG 0, either way. But K1 is less than K at the end, K2. I know that because it's going faster in the end.
Okay.
Yeah? So, work had to be done on our system. And that would be the force of air on the rocket. Like, maybe over here I'll draw a force diagram for the rocket. You got mg down, you got normal up, and you got the force due to air. And I know the air is pushing on the rocket because the rocket is pushing on the air.
Yeah.
It's a third law interaction. So my net force, my vector sum diagram would look like this. I got mg down, I got force due to air, and I got normal. And then so I got this net force to the right. And that's ma, right? So the force due to air is providing my net force. Not normal, not weight. And so work done by air on rocket. And I'm ignoring air resistance. I'm not ignoring air resistance. Because there probably is some. Although it's not going that fast yet, it's probably fast enough for air to start being a factor.
Of course.
But I'm ignoring that. So this is work being added, energy added. And UG is ignored because 0.
So K1 plus work must equal K2.
All right, let's write that. Because the energy flow diagrams really just give you an equation so that you understand the context of what you're solving for. That's what the energy flow diagrams are for.
To solve for weight, we subtract...
Not weight.
To work, we subtract K1 from K2.
Yeah.
Sorry.
And that's what Cynthia was saying. She said work is going to be change in K. And that's really the work energy theorem. But that's another story. I don't have to give it a name right now.
We can solve easy from here. K is equal to...
I don't know anything about F or delta X, but I know the K's.
Yeah.
Right? So now I might as well just solve it. K1 is 1/2 mv squared, which is 1/2. What's the mass?
100, sorry.
100 kilograms?
Yes.
What's speed is 10 meters per second
Squared.
times 10 meters per second? What do you get?
100. 50 times 100.
Is that 100,000 really?
No, it's 10,000. 50 times 100. 50 times 100. Yeah, 5,000, sorry. 5,000.
Thank you. 5,000 what?
Okay, so units.
Yeah,
Seconds,
see we have kilograms meters squared per second squared. See that?
Yeah.
That's the same as kilograms meter per second squared times meter. right?
Okay.
That's the same as a Newton times a meter, which is the same as a joule. You guys good?
Yeah.
So then if you do K2, calculate K2, you get 1/2 mv squared equals 1/2. Mass is still 100?
Yes. And this time our velocity is 20. So 20 squared times 50 is 20,000 joules.
So the work is K2 minus K1, which is
15,000 joules.
yeah, 20,000 joules minus 5,000 joules is 15,000 joules. So that's the work to speed up from 10 to 20, right? Now, what if you're going from like 20 to 30?
Well, when we know that at 20 you're gonna at K2 which is 20,000, right? So we're going from 20 K2 plus work 2 must equal.
So let's
half times.
let K3 equals 30 meter per second.
So K2 plus
So
W.
1/2, so K3 is 1/2 100 kilograms times 30 meter per second times 30 meters per second. What's that going to be?
So 50 times 30 squared. 45,000.
Where's the homie? Where's the homie? Is Manny? There's Manny. Manny's really good too. He'll give you another point of view on the same problems.
45,000.
Okay. So you get what?
45,000.
45,000 joules.
And you subtract K2 from that.
So the work to go from 20 to 30 meters per second, that would be K3 minus K2, right?
Which is 25,000.
So K3 minus K2, what'd you say it was?
25,000.
Is that K3 or K2?
The work.
Oh, that's 45,000 minus
20,000.
45,000 joules minus
20,000 joules.
20,000 joules. And that means you get, so the work to go from 20 to 30 meters per second was what again?
25,000 joules.
Haha.
And this
So you're like, why does that happen? Why does it take so much more energy when your change in velocity is identical?
because of the something you told us in class, at the end of class. Something odd number 0.
If you draw a velocity time graph, these could be any velocities, but this is just 10, 20, 30. What does this look like if you have constant acceleration? And if you have constant acceleration, you have a constant net force, which means force due to air is the same by second law, right? So this would be constant acceleration, right? Which means you have a constant net force. Work is force parallel to the distance you move, right? If force is in the same direction as the distance, you can multiply them, right? Only when they're in the same direction. And in this case, the sled is moving in the same direction the net force is applied.
So we work is in the same direction as force?
Work doesn't really have a direction. It's energy.
Yes.
It's either energy going in or out of your system. But energy goes into your system when your force and your distance, force and displacement are in the same direction.
Okay.
So
what
if this is constant, if your force is constant, as you speed up, do you think that the distance you travel is constant? It's not, right? Hee hee. Take care, homegirl. Hee hee.
Wait, just a side question. If your force is up, like net force, but you're going down, so your energy is leaving your system, right?
Say it again.
If your net force is if your net force is down and you're going up, energy is leaving your system.
If your blah 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 is blah blah blah, but blah blah blah
Let's
blah
say
blah.
you're trying to go up, but gravity's pushing you, but Earth's pushing you down, so you're losing energy, correct?
I'm lost. So you're moving up, and what?
Energy's lost.
If you're moving up, the work done by what? By gravity?
Yeah.
Oh, if you're moving up, the work done by the force of gravity is negative because the force of gravity is down, you're moving up. So you got two ways of approaching that. You can say that you can have the Earth as part of your system, and you can say when you're doing work, you're putting energy in their system in the gravity field, which is part of your system. Or if the gravity field is not part of your system, you can say the force due to gravity is taking energy out of your system. Because if you throw something up, what does it do as it rises?
Slows down.
Why does it slow down? The kinetic energy is taken out by the work done by the force of gravity.
Dissipating.
Yeah. Well, it's not dissipating in that case. It's work. You could say the force due to gravity is doing work because the force due to gravity is opposite the direction you're moving. Most people find that a little weird, so they make the gravity field part of their system, and then you could say that kinetic energy, when you throw something up, is transferred to UG, or gravitational potential energy, after the ball or whatever is at the top of its path and it's not moving anymore. Does that make sense? Anyway, for this one, the force is constant, but as you go faster and faster, you're covering more and more distance, right? So if you count just the triangles, if you just look at the triangles, right? Going from 10 to 20 meters per second is 3 times the energy, right? So let's just say three times. So to go from 0 to 10 takes a certain amount of energy, right? Well, it takes 3 times more energy to go from 10 to 20 meters per second, right?
Yeah.
And then to go from 20 meters per second to 30,
It'll take 5 times as much.
isn't that crazy?
And it'll take 7 times, 9 times.
Isn't that rad?
Yeah.
And that just comes from the fact that you're traveling greater and greater distances. 3 times more work.
So if you went from 10 to 15, it'll take twice as much, right?
Well, in the problem you're given on the worksheet, they're talking about why does it take more energy to go from 20 to 30 meters per second compared to 10 to 20? Well, it's actually 5/3 more energy. If you just count triangles. So it's 5/3 is almost double. So it's almost double the energy to go from 20 to 30 meters per second compared to going from 10 to 20 meters per second. I don't know if that helps, but
Yeah.
talking about a lot more energy. Anyway, I'm gonna stop it, and that was number 2, right?
Number 3. No, sorry, 2.
That was number 2.
Yes.
Let me see if there's any questions. No, I think we're good. All right, so that's 2.